In section 2 of chapter 4, we're going to take a look at applications of exponential functions. We did a little bit of that in section 1. And it's saying here that in many situations in biology, economics, social studies show growth in exponential form. So we'll see that on the next page, where t is often used as time. We'll take a look at some exponential growth functions here in a moment, but we want to know that, or at least be aware, that exponential growth can either get larger or get smaller. And it's basically whether your exponents here are positive or negative or they're fractions that will help determine. So this is in your booklet. Let's take a look at it. We're saying a function of time where y sub o is sort of the beginning. Then there's our e, and then it's by some k value times time. Now when k is greater than 0, it's modeling exponential growth. When k is less than 0, here we're modeling exponential decay. That is, the curve will be going down. Okay, so we'll take a look at this and we'll see some examples. Often it's just substituting into our formula the value we get from our example. So understanding what is here. So let's look at this carefully. Since 1970, the amount of total credit market, that is the debt owed by the government, companies, and individuals, as a percentage of gross domestic product. Now, if you take any economics course, you'll see that GDP, gross domestic product, is an acronym they often use, can be approximated by the exponential function here. F of t yields what it was at some particular year when you're starting, times e, and then to the exponent 0.02t, where t is going to be years. Now, since this is greater than 0, this will indicate some growth. So the year we're starting with here, they're indicating, is 1970. And the amount of what we had at the start of this, the y sub o, is going to be 155% of the GDP in 1970. So find what it would be in 2005. Well, the first thing we need to do is figure out what t is. So we subtract 1970 from 2005, and we end up with 35. And our y sub o is going to be 155. So we can just put this right into our calculator. Let me write it out for you. And if you have a calculator, you should be trying this. So we type in 155, get our function on my TI-84, it's a second function, e, then hit the caret symbol and put a parenthesis. You don't need to put this 0, but you can. 0.02 times 35, that's your t, close parenthesis, and then just hit enter. And it rounds off to approximately 312. So that would be, again, a percent of GDP. Now, if this model remains accurate, what percent of GDP will the total credit market be in the year 2015? Well, here, again, we have to find out what T is. So everything is the same, except our T value changes to 45. And again, I would put this in parentheses and just times that. So you're going to go in your calculator 115, second function E, get E there, caret, and then put this in parentheses, and it gives you approximately 381% of GDP, gross domestic product. Now, as we look at example 2, again, we need to understand what's going on. Here they're talking about cigarette consumption in the United States has been decreasing for some time. So what type of exponent do you think we're going to see there? Well, if we take a quick peek, we see it's negative. So again, that indicates that our K is decreasing here. And then we want to find what year were we starting with? Well, the year 2000. Okay. And find the number of cigarettes consumed in the year 2005, and then later 2010. So this is pretty easy. What will T be here? Well, if it's starting in 2000 and then we're going to 2005, T is going to be 5. Well, here they're using an X, okay. And then this one later will be a 10. Okay, we see that. So then just putting that into our calculator, this second function E, or however you get to it, then caret, and then all of this in parentheses, negative 0.036 times 5, close parenthesis, gives you this approximation. And when you put a 10 there, the same procedure, and again, you should be trying this. This is your practice that gets you ready for your homework, your study plan, your quiz-mes, your practice. Now, for letter B of that, here they're giving us this little graph, but again, they're saying, when will the consumption be 250? Well, we have to use our calculators for that and our tracing tool. And you'll notice that it comes out to be about 15 and a half years from now. So if we're starting at 2000 as our beginning point, adding 15 to that, we get 2015. But again, you may not be able to do this if you don't have this tool. As we look at example 3 in finance, here when money is placed in a bank account and pays compound interest, the amount in the account grows exponentially, as we shall see in chapter 5 that we don't cover, so we'll skip that part. Suppose such an account grows from $1,000 to $1,316 in 7 years. Well, we have the growth function in the form where T is time, Y sub O is our beginning amount, and then B would be our actual rate of interest that we're going to raise to our exponent here. So in a sense, we have two exponents that we're going to deal with. 0, that is when we start, that would be our time, and then 7 years later, which is given there. So if we put a 0 for the T, B to the 0 power is 1. So we're saying if f of 0 is 1,000, and again B to the 0 is 1, we sort of get this to start with, but now our f is going to change to a 7, our value here. So we're going to say b to the 7th power is this amount, which we're saying this here. We're equating 1000 b to the 7th equals this. We're dividing both sides by 1000 to get this. Now, how do we get b by itself? Well, one way to do it would be to take the 7th root of this side and the 7th root of that side. The 7th root of anything that's to the 7th power is just b. And then you might say, well, how can I put that into my calculator? Well, you might remember that there's an exponent here of 1. And to convert from radical expression to fractional exponents, this becomes 1.316. The 1 is the numerator, and then our index number becomes our denominator here. So we just go this, caret, and then put this in parentheses, 1 over 7, and then we get approximately 1.04, as they show here. So the rule then for letter A would be f of t is such that it's 1000 times b now, which is our rate, sort of, raised to the t power. Okay, and I believe this is in your booklet as well. Now, once you have your basic formula, they are asking for part B, how much is in the account after 12 years? Well, you would put t as 12, and this one is pretty straightforward, and you get this. Again, you should be trying these on your calculator. That will help to give you the basis of doing this for your study plan. In example 4, we're looking at data from infant mortality rates in the United States. And we're going to start with the year 1920, where the rate was this. And they're saying let 0 correspond to 1920. Use the data for 1920 and then 2008 to find a function of the form, which is what we had above, that will help model this data. Well, our beginning, you recall, y sub o, is going to be 76.7. And we have then how many years since 2008 from 1920? Well, that's 88 years. So we can start to set it up. And as you can see, we have this when this is 0, as from before. And then in your booklet you can still see this, that this, with our time of 88 years, equals this new rate. So we're going to divide both sides, as they show here, by 76.7, 76.7. And now we have just this remaining. And how do we get this? Well, we're going to take the 88th root of this side and the 88th root of that side. But the convenient way to do it, of course, this then becomes just b, is to take this and again the exponent here is 1 on top, and then our index number of our radical sign becomes our denominator. Now they're showing it here quite nicely here, but I wanted you to see the process. So in parentheses I would put this, then I would use a caret, and then in parentheses I would put that, and you should get then approximately this. So the function then is this. Now again, they're using exponential regression on a graphing calculator to graph our data, and it comes somewhat close. So if you do some rounding, it varies just a little bit, but very, very close. All right, and then it says use the preceding model and assume they continue to remain accurate to estimate the infant mortality in this year and this year. So again, our times would be 92 and 95. And these are the values that we get. In example 5, related to business, sales of a new product often grow rapidly at first and then begin to level off with time. Suppose the annual sales of an inexpensive can opener are given by this. So as we look at it, we see this, but then now note that within a parenthesis, we have negative e and also a negative exponent. So a little bit tricky putting that into your calculator, but hopefully following through. What were the sales of the first 3 years? Well, here of course x will be 1, and then doing so you get this. X will be 2. Notice there's an increase. X will be 3. Notice there was a sharp increase initially, but now it's tapering down. And then what were the sales at the end of the 10th year? And we will give you time to try these in your calculator. Now on the next slide we're going to show you the graph of this. Now I tried these on my calculator, this last one here particularly, and then here it is a negative, minus, and then e, and then all of this in parentheses after we use the caret, and then close parenthesis, and I got that. I didn't get it the first time because I had the wrong negative sign. So again, you need to practice so you get what you're supposed to. The calculator only does what you tell it to do, and if you put in wrong data, of course, it won't react properly. Now here is the graph of example 5. As we look at it, we see again sharp growth initially, and then a leveling off. And where does it level off to? Well, according to our text here, it's leveling off to around 10,000 per year after the 12th year or so. Okay, a variety of activities can be modeled by logistic functions whose rule forms this. The logistic function is, in the next example, is sometimes called a forgetting curve. All right, let's take a look at this. Now, forgetting curve I can think of it as spring and Thanksgiving break, winter break, that as you don't practice something, there is a sharp loss of things, as we'll see later in the curve. So keep that in mind, that over holidays, you can't say, well, I'm going to just not do anything. You have to kind of keep your mind active so that you know about these things, because there is a memory loss curve as time goes by. So they did some experiments about how many facts were remembered at the beginning of the experiment. Well, they found that when t, or time, was 0, you remembered 10 facts. Now, how about when t is 1 week, that is 7 days, and then later 14 days? Well, again, when you put that into your calculator, it ends up being not 10 anymore after 7 days, but let's say 9. And then after 2 weeks, you may have forgotten it all. So we speak of, in psychology, short-term memory and then long-term memory. That one of my colleagues, back when I taught high school, said that in order to remember something, you have to say it or teach it 7 times so the students get that drill. And this is what you're getting as you do your study plan and practice and write things out, because also writing things out is another way to add to memory. Okay, I won't make this a psychology class, but that's what we see. And then this is the curve. So what are we thinking? Well, you might remember then, out of many facts that you were taught, 10, and then, you remember it for a few days, and then there's a rapid drop. Well, here is spring break, you see, and Thanksgiving break a little bit, and winter break, and summer break. Wow. That's why if you know something, and it's in your long-term memory, then that's not a new fact. But new things that you've been exposed to, you want to treat in such a way that you get reinforcement. All right. Who would have imagined that we had something like that this far into our course? Okay, there are some exercises, and we'll be checking this out, and hopefully through practice, homework lab log checks, that you're writing it out neatly and clearly, orderly. This is all part of your end of semester grade.